Okay, so good morning, everyone. So welcome to today's lecture. The topic of today's lecture would be about the LU factorization of a matrix. So let's get started by discussing about definition of the LU factorization. Okay, so first of all, an LU factorization of a matrix. Okay. It involves writing the matrix as the product of a matrix L and a matrix U, such that, okay, so there are some requirements for the matrix L and matrix U. So here L is a lower triangular matrix. Which has the main diagonal consisting only one. Okay, this means that all the entries that the main diagonal of the L matrix is 1. Okay, and U is an upper triangular matrix. So this is a definition for an LU factorization of a matrix. Okay, so the question is, why would people care about the factorization, specifically the LU factorization of a matrix? So it is pretty simple because people have shown that many matrices can be rewritten in this form. And when a specific matrix A can be rewritten in this form, when a matrix A can be rewritten in this form, it is really helpful in solving the linear system of linear equation AX equals B. Because when we factorize A as LU, we are only working with triangular matrices L and triangular matrix U, which is a lot easier to work with compared to the original matrix A, because as we already know, triangular matrix, half of the entries in the triangular matrix are 0. So it is easier to work with triangular matrices compared to the original general matrix. Okay, so we will talk about the application of the factorization later in solving the system of linear equation today. So with all of this property, people would be interested in learning how to find the LU factorization of a matrix. But before we get into that part, I want to emphasize that not all matrix has an LU factorization. Even though a lot of the matrices, you can factorize it as an LU factorization, but not all of the matrix has an LU factorization. And people also was able to show that the matrices, okay, let's write it over here. What do you want next? Okay, the matrices having an LU factorization are matrices with property okay, I'm gonna call this property star. Okay, the probability of the matrix to have an LU factorization is that the well-reduced echelon form of the matrix is achieved without rows. Okay, so we have learned about the reduced row echelon form of a specific matrix last week, and we already know in order to transform a matrix to it reduced row echelon form, we have to use the rows operation, including three types. The first one is to switching rows. The second one is to multiply any row with a scalar, and the third one is to adding a multiple of any row to another row. Okay, so the matrices with the property that its reduced row echelon form is achieved without switching rows will definitely have an LU factorization. And we're not gonna prove this, but keep in mind, okay? So let's talk about finding the LU factorization of a matrix, and let's start with an example, okay? So given a matrix A, let's start with an example. Given a matrix A, this is a 3 by 3 matrix, 1, 2, 3, 2, 3, 1, and -2, 3, -2. Okay, the problem is trying to find the LU factorization of this matrix. Okay, so there will be several approaches to this problem. Okay, so there would be some approaches to this problem. So our first approach is to use the definition only. So according to the definition, an LU factorization of a matrix is rewriting that matrix as a product of a lower triangular matrix L with an upper triangular matrix U, such that the main diagonal entries in L are ones. Okay, so let's suppose that we can find an LU factorization for this matrix A. I'm gonna rewrite this as a product of a matrix L and a matrix U. Okay. Okay, so suppose A is equal to the product of these two matrices. So first of all, L is a lower triangular matrix, and we already know that a lower triangular matrix are the matrix that the entry above the main diagonal are 0. Okay, so we should have 0 here, 0 here, 0. Oh, and I forgot to mention, because here A is a 3 by 3 matrix, then you should have L and U are also 3 by 3 matrices too. Okay, so L is a lower triangular matrix, so we should have 0, 0, 0 here. And also the main diagonal entries are 1, so we should have 1, 1, 1. Opposed to LU is an upper triangular matrix, so we should have the entries below the main diagonal to be 0. Okay, so here for you, we should have the 0, 0, 0. So we have 3 unknown entries here, and we have 6 unknown entries on the right matrix. So we are calling some variable here. So let's call them A, B, C, D, E, F, G, H, and K. Okay, so we are supposing A is equal to the product of a matrix in the form of the L matrix and a matrix in the form of the U matrix. Okay, so here we got a product of 2 matrices. Actually, you can multiply these matrices together and you can compare the results with the matrix A. We talked about the equality of 2 matrices before. Okay, so 2 matrices are equal to each other if they are identical, meaning that each entries are equal to each other. So as you can see, because A is a 3 by 3 matrix, so we have 9 entries in total. So by comparing these 9 entries with the 9 entries of the resulting matrix, you would be able to establish a system of linear equation. Okay, you will be able to establish a system of linear equation. Okay, as you should see that here we got 9 variables. 1, 2, 3. We got 3 here, we got 6 more, so we got 9 variables. And we got 9 equations. So theoretically, we would be able to solve for this system of linear equation, right? Theoretically, we can solve this system of linear equation. We have learned the method to solve that already. But as you can see, a system with 9 variables and 9 equations are too much. Okay, so this approach might be not the best way to find an LU factorization for a matrix. Okay, so this first approach is based entirely on the definition only, but we will use another approach and we will call this method the multiplier method. Okay, so before we apply this method to the matrix A over here, first of all, I will explain about a little bit about the background of this method. Okay, so let's start with a matrix A. Suppose A has property star. Okay, suppose we got a matrix A with the property stars. The property stars here meaning that the reduced row echelon form of the matrix is achieved without switching rows. Okay, so in that case, when you are trying to transform A into its row echelon form, we only need to use the second type and the third type of row operation, or multiplying any row with a scalar or adding a multiple of any row to another row. Okay. So with that in mind, for any matrix A with property star, you would be able to transform A into a matrix U, where U is an upper triangular matrix. Keep in mind that a row echelon form is actually an upper triangular matrix, but here we don't need the leading entries to be 1. Okay, so we don't need the leading entries to be 1. So U here can actually be the row echelon form of the matrix A. And remember, when we are transforming any matrix to its row echelon form, we are actually applying some types of row operation to that matrix, right? And we have discussed this previously last week, that when we are performing the row operation to any matrix, actually we are multiplying that matrix with an elementary matrix corresponding to that specific row operation. Okay, so suppose that after we have performed several row operations to matrix A, suppose I am applying E1, E2 up to EK to matrix A, and I receive the upper triangular matrix form of A, which I will call U. Okay, and we have also learned previously that any elementary matrices will have an inverse, and the inverse of those matrices are actually elementary matrix too. We discussed this last week. So because of that property, I can multiply both sides with the inverse of this elementary matrix, and you should be able to reconstruct matrix A from matrix U. So here we should have A equals to E1 negative. Okay, so first of all, I'm going to multiply both sides with E1 inverse first. And then we got E2 inverse, and so on, until E3 inverse. Right? Okay. And keep in mind that because A has the property star, so meaning that we don't have to use any switching row operation. We are only multiplying a row with a number, or we are adding we are only adding a multiple of a row to another row. Okay, so that guarantees that those elementary matrices are lower triangular matrices. Because remember that elementary matrix is obtained when you are applying some kind of row operation to the identity, right? Like for example, here I got an identity. This is the identity matrix. Initially, the identity is a lower triangular matrix already. So if you like, for example, I'm multiplying the first row with number 2, it is still a lower triangular matrix. If I am adding a multiple of the first row to the third one, for example, it is still a lower triangular matrix. Okay, and keep in mind that if you are trying to transform a matrix to the upper triangular form of that matrix, we are only adding a multiple of a row to a row below that row. Okay, so for example, I'm multiplying the first row and I'm adding that to the third row. We are not gonna ever multiply the third row and adding that back to the first row. Okay, we are only multiplying a row and adding that to a row below that. Okay, so with all of these property, it is guaranteed that all of these elementary matrices are lower triangular matrices. And you should be able to show that the inverse of those elementary matrices are also lower triangular matrices. And when you are taking the product of many lower triangular matrices, the product itself is also a lower triangular matrix. Okay, so in this case, I can find the product of these matrices and I will denote that as L, which stands for a lower triangular matrix. So that is basically what people call the multiplier method. Okay, so how to actually apply this method in finding the LU factorization of this matrix A over here. Okay, let's start. So first of all, I am going to rewrite the matrix A in the form of identity multiply itself. So we should already know that when you multiply the identity matrix with any matrix, we got itself, right? So let's start with rewriting the matrix A as the product of the identity and itself. Okay, and we will try to transform the, okay, so here the matrix on the left is already a lower triangular matrix. So we are trying to transform the matrix on the right to become an upper triangular matrix by applying some kind of row operation. Okay, so each time you apply a row operation to the matrix on the right, you will apply the inverse operation of that specific operation to the matrix on the left. Like for example, if you are multiplying any row on the right by 2, then you multiply the corresponding row on the left by 1/2. Okay, so that's what we're gonna do. Okay, so let's start. So here the matrix on the right, the leading entry of the first row is already 1. And we are trying to transform this into the upper triangular matrix. So we need to change these entries 0 to become 0, right? So for example, if I want this entry below the entry number 1 to become 0, I am multiplying the first row with -2, and then I am adding that to the second, right? I am multiplying the first row with -2 and adding that to the second row. So you should have 1, 2, 3. So this should become 0. 1 -2 plus 2 is 0. -4 plus 3 is -1. -6 plus 1 is -5. Right? And because we are applying some kind of row operation to the right matrix, we need to apply the inverse of that row operation to the left matrix. Okay, so you are multiplying the first row by -2 and adding that to the second row. So on the left matrix, I'm going to multiply the first row with -2 and adding that to the second row. So I should have 1, 0, 0, -2, 1, 0 on the left matrix. Okay, that's what we're gonna do. Oh, I'm sorry. So this should be 2 because we are multiplying this one. Okay, next for the third row, in order to erase this entry over here, I'm gonna multiply the first row with 2 and add that to the third row, right? Multiply the first one with 2 and add that to the third row. Okay, so 1 multiplied 2 is 2 plus -2. This should be 0. 2 multiplied 2 is 4. Add that to 3. It should be 7. And 3 multiplied 2 is 6. Add that to -2. You should have 4. Right? And the same things happen for the matrix on the left. On the right matrix, we are multiplying the first row with 2, add that to the third one. So on the left matrix, we are multiplying the first row with -2 and add that to the third one. So this should be -2, 0, 1. Right, question?
In the second row, why isn't it -2? Sorry, the first column, second row.
This one?
Yeah.
Okay, so basically, okay, so for the first operation, I am multiplying the first row with -2 and add that to the second row, right? So I am taking -2 multiplied by the first row and then I'm adding that to the second row. This is the notation for that operation. We will discuss about this last week. So because I am applying this matrix to the matrix on the right, I need to apply the inverse of this matrix to the matrix on the left. So the inverse of this specific matrix is actually you are taking the first row, you multiply that with 2, and then you add that to the second row. Right, so I am taking the first row and multiplying that by 2. You should have 2, 0, 0, and then you add that to 0, 1, 0. You should have 2, 1, 0. The same things happen for the pair of first row and third row too. For the pair of third row and the first row and third row, I am multiplying the first row with 2, add that to the third row. So on the left matrix, I'm multiplying the first row with -2. And then I'm adding that to the third. Okay. That's what I have done. Okay, so the matrix on the right is still not an upper triangular matrix. So we need to perform the row operation one more time. But this time I will multiply the second row with 7. And then I'm adding that to the third row. Okay, so now A should be equal to okay, so -1 multiply 7 is -7, add that to 7, you got 0, right? And -5 multiply 7 is -35. Add that to 4, you got -31. So conversely, you are multiplying the second row with 7, add that to the third row. On the left matrix, you will multiply the second row with -7 and add that to the third. Okay, so be careful at this step because you might make some mistake. So I am saying that you are multiplying the second row with -7 and then you add that to the third row, right? But you only change this value over here. These values are fixed now. You only change this value over here. So we are going to multiply 1 by -7 and add that to the second row. So this should be the final matrix. Okay. Keep in mind that we are only changing the entries of these. We're only changing these entries, and once the entry I change, it will fix. Don't change it once again. Okay, just change the entry that previously 0. Change that. Once the entry and no longer 0, keep the entry, don't fix that anymore, okay? Yeah, so as you can see here, the matrix on the left is a lower triangular matrix with the main diagonal consisting only one, and the matrix on the right hand side is an upper triangular. So this is an LU factorization of the matrix A over here. Okay. Okay, so do you have any question about the multiply method? That is called the multiply method. Okay, is there any question? Okay, if not, then we're going to move on to the next part, which is about the application of the LU factorization in solving the linear system of equation. Okay. What should we erase? Can I erase this one? Okay, so just as I have mentioned, for the next part, we will learn how to use the LU factorization of a matrix in solving a system of linear equations. Okay, so like for example, here we are trying to solve the system of AX equals B, where A is the original matrix. Okay, where A is this matrix, and B is the matrix 1, 2, 3, the column vector 1, 2, 3. Okay, so let's rewrite this as this one. So X should also be a column vector. So let's call it X1, X2, X3. Or should I call? Oh, yeah. And B is a matrix 1, 2, 3. Okay, let's try to solve this system of linear equation. A multiply the column vector X equals to the column vector 1, 2, 3. Okay. So we have been able to factorize A in this form of the LU factorization, right? So first of all, I'm gonna put this form back to this system of linear equation. Okay, so now we should have 1, 0, 0, 1, 1, 2, 2, 7. X1, X2, X. Okay, so I am replacing A with its LU factorization form. And okay, so let's talk about the product of the matrix in the middle with the X matrix, right? So this is a 3 by 3 matrix. This is a column, a 3 by 1 matrix. So the product of these matrix should be a column vector, right? So let's denote this as the column vector y1, y2, y3. So in this case, you should have the product of the matrix on the left with this Y matrix equals to the matrix 1, 2, 3. Right? So I am going to perform the matrix multiplication and I will try to solve Y1, Y2, Y3. Okay? Multiply this. Okay? So when we are multiplying a matrix with another matrix, simply multiplying the row of the first matrix with the column in the second matrix, right? So we should have y multiply y1. 0, 0 multiply anything is 0. So we should have y1 equals to the first entry on the right, which is 1. And similarly, for the next equation, you should have 2y1 plus y2 equals 2. And the last one should be negative 2y1, negative 7y2 plus y3 equals 2. Right, any question with the matrix? Okay, so at this point, you should be able to see why people are interested in triangular matrix. Because when you multiply a triangular matrix with a column of variable, the corresponding system of linear equations is extremely easy to solve because you already got one variable, you plug that value into another equation, and you should be able to find another value, right? So here we got y1 equals 1, so let's keep that y1 equals 1. And then let's plug this into the second equation. So 2y1 now become 2. And then I'm gonna cancel the 2 on both sides, so you should have y2 equals 0. Right? And plug all of that into the final equations. This should be -2, this should be 0. So -2 plus y3 is equal to 3, right? -2 plus y3 is equal to 3. So y3 should be equal to 5. Right? Y3 should be equals to 5. Any question? Okay, so you are now able to find the value of y1, y2, y3. So this vector over here is equal to the vector 1, 0, 5. Okay, so now we only need to find the value of x1, x2, x3. So the same things happen here. Now I'm going to multiply this matrix here with this matrix here, and then I'm going to compare the results with this column matrix 105. And once again, because the matrix in the middle is also a triangular matrix, so you should expect to have some kind of system like this one. Okay, so so here we should have 1x1 plus 2x2 plus 3x3. That should be equal to 1, right? Next, we should have -1x2, -5x3. It should be equal to 0. And last but not least, -31x3 should be equal to 5. Right? And now you should be able to solve for the value of x1, x2, x3. It is pretty easy to do, right? So first of all, let's find x3. It is the easiest value to find. X3 should be equal to -5 over 31. Right? And from the second equation, you should have x2 equals to 5x3. So it should be equal to -35 over -25 over 31, right? Oh, I'm sorry. We got a negative sign over here, so no more negative sign. Sorry. X2 should be equals to -5x3 and x1 for x1. So according to the first equation, x1 is equal to 1 minus 2x2 minus 3x3. So this is actually equals to 1. -2x2 is actually -50 over 31. -3x3 is actually 15/31. Right? So finding the common denominator is 31. On the numerator, you should have 31 minus 50 plus 15. Right, you should be able to calculate this, right? So 31 plus 15 is 46. 46 minus 50 is -4. So -4 only. So you have been able to solve the system of linear equation already. Okay, so do you guys have any question? Okay, that's good. Yeah, if you don't have any questions, so that's all the lecture for today.